Hello and welcome to another video lesson with Lawson. Today we're going to continue talking about some of the fundamental concepts related to calculus that we'll be using in this course. After being introduced to how to find the derivative of a function and being able to apply that and being able to find that derivative at a specific value, we have to be able to look at the opposite process, antiderivative or the integral. We're going to talk about integrating a function to be able to use the integral to describe a certain property or something that's related to the universe. An antiderivative really is what it sounds like. It's the opposite of a derivative. We're going to see what that means, and we're going to start by defining the antiderivative. We have a continuous function, capital F of x, whose derivative is lowercase f of x. Then the antiderivative of that lowercase f of x is capital F of x. So what we're really saying is that if we were to take the antiderivative of the derivative of that function, we would get back the original function. Integral sign, you see over here, looks kind of like a stretched out S. And what we find that's different about integration than derivatives is with the derivative, you get a single derivative based on the function. With an integration, you get a family of antiderivatives, because when you integrate, that line can actually be anywhere along that vertical axis. Just simply by adding a positive or negative constant, you can shift that line up or down, and you would still get the same change in y for change in x along that function. When we're doing indefinite integrals, we get a family of functions that all have the same derivative, and we note that by adding that constant c. While it's important to be able to describe or understand what an indefinite integral is, since the majority of the time we'll be using definite or bound integrals, that's the more important concept for us. What we do with the bound integral is we have a lower and an upper boundary that determines where we're trying to find the integration of that function for between two input values. In this case, we're denoting the input value that's the lower bound is a, and the input value that's the upper bound is b. We're going to take that bound part of the function, and we're going to break it up into smaller and smaller pieces, into infinitesimally small pieces, and find what each point gives us, and then sum all of those points up. And you see it visually, it's much more straightforward or much easier to try and make sense out of. A graph represents the function f of x. An indefinite integral, we would just find the integral of the function and then add that constant c. We identify where the lower and upper bounds here are shown. In this case, the vertical yellow line on this side, that's the lower boundary that's closer to 0. Over here on this side, that's the upper boundary that's further away from 0. And then we break those into smaller and smaller pieces. So we're going to show first breaking it into relatively small chunks, and each one of these rectangles represents part of what is bound between the function and the x-axis. There's some error. You notice on this side, we've got some of them sticking up over the function, and on this side we've got some that are down below the function. And so that error is an issue, and what we do is we make the width of each one of these boundaries smaller and smaller, and that's why we're taking this as n goes to infinity. As we make this an infinite number of segments, eventually, since it's an infinite number of segments, each one of those segments only goes up to the function and doesn't have anything that sticks up above or below it, so we end up not having any of that error in our final answer. Integral of a function, of a bound function, represents an area between the function and the x-axis. And so here's how we're going to denote our integral. This is going to be our integral notation. We have that integration sign. We have the lower boundary, we have the upper boundary, we have the function that we're integrating, and then the variable we're integrating in terms of. So this would be read, the integral of f of x in terms of x between a and b, or from a to b. The upper limit on this positive axis is going to be further away from 0, and the lower limit is going to be closer to 0. Really what we're going to find is what is the function of integration, what it computes to be at the upper boundary, what it computes to be at the lower boundary, and take the difference between those two. We're going to go over several important rules that you'll want to memorize and be able to apply throughout the course. First, we're going to talk about the rules for integrating a constant, the rules for integrating a variable, and the rule for integrating a power. These should be pretty obvious and pretty straightforward, because we went over the rules for derivatives of these, and the antiderivative is basically going backwards. The rule for integrating a constant is we need something that when we take the derivative, we will get the constant alone back out. And so when you have a variable, the derivative of a variable is 1, so a constant times 1 would be that constant. That's why the antiderivative, or the integral of a constant, is the constant times a variable. In this case, we're taking the integral of a constant in terms of x. The antiderivative would be that constant times that variable x plus c, because these are indefinite integrals. If it was a definite integral, we'd have to have a lower and upper boundary, and we'd input the upper and lower boundary for the two functions and then find the difference. So it would be c times b for the upper boundary, c times a for the lower boundary, and c times b minus c times a would be our definite integral if we were applying the rules, or if we were applying the lower and upper boundary that we're used to seeing. When we have a variable x, we need a function that the derivative would give us back that variable x. The variable x can be taken from x squared almost. Derivative of x squared would be 2x. So we just need to get rid of that 2, and the way we do that is by dividing by 2. So when we have a variable alone, in this case we're doing the integral of x in terms of x, the antiderivative, or integral function, will be x squared divided by 2, and since we don't have a lower and upper boundary, we have to add that constant to represent the family of antiderivatives. The power rule shows that if you're trying to find the integral of a variable to a power that's a constant, in this case represented as the variable n, in terms of that base variable, then we would take that base variable and raise it to the power plus 1 and divide that by that power plus 1, so that when we take the derivative, it ends up dropping down and being divided by n plus 1 and cancels out, leaving just the variable to that power as our derivative. And of course, because this is an indefinite integral, again, we have to add that constant c, because it's a family of integrals that we get when we don't have an upper or lower boundary. Let's look at some examples for each of these. First, I'm going to integrate 3 in terms of x. 3 is a constant. The integral of that is 3x plus c. And we should be able to easily see that the derivative of a constant is 0, so c would go to 0. 3x, the derivative is 3, so if we were to take the derivative of this function, we would get back 3. Therefore, 3x plus c is the antiderivative of 3. Let's integrate v in terms of v. Now I'm going to get the variable by itself as the derivative, and so that would be v squared divided by 2 plus c. Let's look at the integral of t to the 7th in terms of t. Now I need an antiderivative, a function that if I were to take the derivative, I would get back t to the 7th. That's t to the 7 plus 1 divided by 7 plus 1 plus c, or t to the 8th divided by 8 plus c. And note that the power rule, there's one instance that you cannot apply it, and that's when the power is -1. Because if you had -1 and then you divided -1 plus 1, you would get 0. Any value divided by 0 is undefined. Now let's look at what we would do if we were working with the natural log. The derivative of e to the x is e to the x. That means the antiderivative of e to the x is e to the x. We just have to remember to add that constant c. If we could have e to a power of a constant times x, it actually is going to turn out, this is an example of a substitution problem, but instead of having to review and go through the substitution problem, which we haven't actually gone over yet, we're going to just go over this as one of the rules that you can memorize, and it might be a little bit easier than trying to apply the substitution to it every time you run into this. E to a constant times x, the integration of that is 1 over that constant times e to the constant times x. When we have 1 over x, the integral of 1 over x is the natural log of the absolute value of x plus c. Not too difficult to see that because we talked again about the derivatives of these in those cases. The derivative of the natural log of x was 1 over x, so it makes sense that the antiderivative of 1 over x is the natural log of x. Patterns that you see here when we look at the trigonometry functions, when we're integrating cosine of x in terms of x, we get back sine of x and cosine of a times x. The integration of that in terms of x is 1 over a times the sine of a times x. We see a similar pattern when we're looking at the integral of sine. The integral of sine of x in terms of x is negative cosine of x. The derivative of cosine is negative sine. We need that negative out in front, that -1, that constant that we multiply to be able to make it so that the negative disappears, since we are integrating sine, not negative sine. When we're integrating sine of a constant times the variable x, we have to remember again we need that constant to not be there when we're taking the derivative of the antiderivative. So it's -1 over that constant, in this case represented as a, times the cosine of that constant a times that variable x, plus c, because we're representing the entire family of antiderivatives at this time. Let's integrate e to the k in terms of k. Integrating e to the k in terms of k gives us back e to the k, but because it's a whole family of antiderivatives, we have to include that constant at this time. When we're looking at integrating e to a constant times a variable in terms of that variable, we have 1 over that variable times e to the variable times the constant, and again because it's an entire family of antiderivatives, plus the constant. We're going to integrate 1 over r in terms of r. The antiderivative of 1 over r is natural log of the absolute value of r. And again, because it's an indefinite integral, we have to remember to include that unknown constant. If I'm integrating the cosine of theta in terms of theta, it is going to be the sine of theta plus that constant. If I'm integrating cosine of 6 theta in terms of theta, that's going to be 1/6 of the sine of 6 theta plus the constant. The integral of sine of phi in terms of phi is equal to the negative cosine of phi plus c. Be a little bit careful when you're working with this, because the derivative of cosine is negative sine, but the antiderivative of sine is negative cosine. Just a little issue that can present itself once in a while. If I was going to integrate the sine of 9 phi in terms of phi, that's going to be negative 1/9 of the cosine of 9 phi. Finally, we're going to look at doing the integration or finding the integrals of slightly more complex situations. First, a relatively straightforward one, which is a constant of product, or where we have a product times a function that we're taking the integral or trying to find the integral of. Then we'll look at the sum and difference. That's where we're either adding or subtracting two functions from each other and trying to find the integral of those. The substitution, which is like the integration of a function within a function. We did the derivative of a function within a function, and we saw that chain rule. In this case, we call it substitution when we're finding the antiderivative of a function within a function. It can be a little bit complicated and confusing when you first see it, but with practice it gets relatively easy. It's a constant product rule. When you have a function and you're multiplying it by a constant, just like we saw with derivatives, we can actually take that constant and factor it out, find the derivative, and then still multiply it by that same constant. The same is true here. We can factor out that constant and take the antiderivative or find the integral and then multiply it by that constant. So it turns out the constant can simply be factored out of the process to make things relatively easy for us. For the sum and difference, we would take the integral of one function and then the integral of the other function, and if we were summing them together, sum their integrals, or if we're finding the difference between them, taking the difference of their integrals. And then, of course, adding that constant c when it's an indefinite integral, as we're seeing here. We use substitution to represent the internal function, and then we can integrate that substituted variable u in terms of u. This part is really one of those situations where seeing this one example is not going to encompass it very well. You're going to need to see several examples and need to practice several versions of it before you're going to get comfortable with the idea of how to do integration and through substitution, much in the same way to find derivatives using the chain rule or the function within a function or the composite rule will also take practice to get very skilled at. Let's look at an example of the constant product. Let's integrate 2 times x to the fifth in terms of x. What we see here is this constant 2. This is really 2 times the integral of x to the fifth in terms of x. X to the fifth is a power. The integral of the power is x to the n plus 1 divided by n plus 1. So this will be 2 times x to the sixth divided by 6. 2 sixths is 1/3. X to the sixth divided by 3. Instead of doing a sum and a difference, we're simply going to do a sum. Let's find the integral of a plus a cubed, or to the third power, in terms of a. This is going to be the integral of a in terms of a plus the integral of a to the third in terms of a. A is a variable, so the integral of that is going to be a squared divided by 2. A to the third is a power, so the integral of that is going to be a to the power plus 1, 4, divided by the power plus 1, or 4, and then we have to add to the constant c. As our first introduction to the substitution process, we're going to do a relatively straightforward example. Let's find the integral of 4q plus 7 to the 8th in terms of q. If we make u equal to 4q plus 7, then we can do the integral of u to the 8th in terms of q. There's a little bit of an issue here, though. We're trying to integrate u in terms of q, and we can't because u is not q. Those are different variables. However, we see what u is equal to up here, and we can find the derivative of u in terms of q. The derivative of constant 7 is 0. The derivative of 4q is 4 times 1 times q to the 0, which is 1. So this ends up being 4. Just a little algebra here. That means the derivative of u in terms of q is equal to 4. In terms of q, if we're doing the lowercase delta q, that is going to equal 1/4 of du, or du divided by 4. Now we see a way of being able to get rid of this dq. The integral of u to the 8th, or in terms of u divided by 4. And the integral of u to the 8th in terms of u, it's pretty straightforward because that's just simply the power rule. So this ends up being u to the 9th divided by 9 divided by 4 plus c. Of course, we can do a little bit of cleaning up of that. This ends up actually equaling u to the 9th divided by 36 plus c, and u is 4q plus 7. So our actual statement of what this integral is 4q plus 7 to the 9th divided by 36.